Good afternoon and welcome to the 2020 Annual Conference Webinar Series. This webinar is part of an 8-part series, and to begin, I'd like to thank our series sponsors, Thompson & Associates, Hyatt Survey, Kimley Horn, Iron Ridge, Infrastructure Consulting and Engineering, TLP Engineering Consultants, ACEC Retirement Trust, Collinsworth Insurance, Florida Concrete Pipe Association, WGI, Mock Ruse and Associates, Nova Consulting, T.Y. Lin International, and Culpepper and Turpinning for supporting the series. Today's webinar is 3D bridge modeling, a case study presented by Ms. Kaylee McNeile and Mr. David Lutz. When this webinar is complete, a short survey will appear for you to click on. For those of you interested in getting PDH credit, please ensure that you complete this survey in its entirety. We will process PDHs in approximately 7 to 10 business days, after which you will receive an email with instructions on how to access your certificate. During the webinar, if you have a question, you can use the chat feature and we will answer those at the end of the presentation. With that, I'd like to introduce our speakers. Ms. Kaylee McNeile is a project engineer with WGI and a graduate of the University of Central Florida. She has been with WGI for 4 years, starting in the roadway division and transferring to the structures division after 2 years. She has been involved with Open Roads and OpenBridge since the first year of her career. She has used these programs to help with engineering decisions on active projects and to strengthen project pursuit efforts. David is a project engineer with WGI and a graduate of University of Central Florida and the University of South Florida. David has been with WGI for over 7 years with experience in bridge, roadway, and toll gantry design. Bridge structural experience includes steel box girders, steel plate girders, pre-stressed concrete beams, reinforced concrete flat slabs, pre-stressed concrete slab units, and miscellaneous structures. He has experience in toll facility design for Florida's Turnpike and plans production to FDOT or related agency standards. At this time, I would like to turn it over to Kaylee and David.
Thank you, Stephanie. Good afternoon, everybody. I want to first thank you all for attending our presentation today. During these unprecedented times, I hope everyone is staying safe and healthy. Today's presentation will focus on the real-world benefits and challenges of utilizing Bentley's OpenBridge modeler on some of WGI's FDOT projects and pursuits. We will go through the numerous applications of OpenBridge modeler, including graphic development, projects with complex construction, complex bridge geometry, multidiscipline coordination, and demonstrate how OpenBridge integrates with OpenRoads. We will also discuss Bentley's latest developments, including OpenBridge Designer and plans production utilizing FDOT Workspace. With that being said, let's go ahead and get started. So like Stephanie said, my name is David Lutz. I'm a structural engineer with WGI in the Tampa office. In my 7 years at WGI, I've had the opportunity to work on complex steel bridges, complex concrete bridges, and I've worked on toll facilities with Florida's Turnpike as well as miscellaneous structures.
And my name is Callie McNeile. I've been with WGI for nearly 5 years out of the Fort Lauderdale office, and I've had the opportunity to work on concrete bridges, miscellaneous structures, and various projects with the FDOT and Florida's Turnpike.
The agenda for today's presentation will go through WGI's background and history, who we are as a company. We'll discuss historically the traditional bridge design process and its associated challenges. We'll then discuss a number of WGI's projects and pursuits we've utilized OpenBridge modeler on. We'll talk about some of our observations and lessons learned, as well as some of the challenges we've experienced on those projects and pursuits. At the end of the presentation, we should have plenty of time for Q&A. So a little bit about WGI. WGI was founded in 1991 in West Palm, Florida, where headquarters remains today. We have 18 offices nationally, with 8 located in Florida. We're a firm of approximately 675 people with 400 in Florida. WGI proudly services private clients, public agencies, and municipalities. We have won work with every FDOT district as well as central office. WGI is known for delivering design-build projects, as we have won more than 40 projects valued at over $1.7 billion in Florida alone. Most recently, WGI was selected to lead a 3D pilot project with Florida's Turnpike Enterprise, or FTE. With this project, WGI will develop 3D tools and processes to help the owner review 3D models We will develop checking and QCing procedures for 3D models, as well as provide beneficial 3D information in terms of permit coordination, public hearings, and higher level presentation material by referencing all design components of our project into one model. This includes bridges, drainage, signing, lighting, utilities, signals, tolls, right-of-way, and existing digital terrain information. We'll also be exploring the 3D benefits for Florida Turnpike's maintenance department by providing additional 3D bridge information. So historically, traditional bridge design has followed a similar path. First, your roadway engineer will develop their horizontal and vertical geometry in 2D CAD. Then the structural engineer will come in and lay out their bridge geometry. Some preliminary calculations may be performed, like vertical clearance, to verify preliminary geometry. The structural engineer will then coordinate the results with the roadway engineer, which typically triggers rework of that initial geometry. Once the initial geometry has been reviewed, the structural engineer can proceed with the remaining bridge design, like substructure calculations, superstructure calculations, finish grade, and constructability reviews. The geometric information will be taken from CAD and re-entered into input and design spreadsheets, and then sometimes re-entered another time into design software of choice. After these calculations and reviews have been performed, based on those results, there may be another round of coordination with the roadway engineer. Throughout this iterative process, 2D plan production is ongoing and may require multiple rounds of revisions as they are dependent on the geometry. Once plans have been completed, review of the 2D plans in accordance with the governing criteria can commence. The obvious disadvantages of this approach is that there is multiple manual data transfer with roadway and other disciplines, repetitive data entry between numerous design calculations, spreadsheets, software, and plans. With this iterative process, there is no quick or efficient change management when horizontal or vertical geometry is updated. There are translation issues between CAD, modeling, and design calculations, and there is virtually no automation for CAD production or design. So OpenBridge Modeler, or OBM, looks to remove the disadvantages I previously discussed and enhance the bridge design process by continuously exchanging project information from initial geometry all the way to final design. This exchange of information includes horizontal and vertical roadway geometry, bridge geometry, and it even includes beam strand patterns and bridge reinforcement. This all-inclusive approach looks to improve decision-making processes. OBM helps streamline real-time collaboration between disciplines, as well as sharing, reusing, and repurposing existing data to minimize risk of design errors, as well as helping to identify construction issues. The advantages of OpenBridge Modeler are that you're able to leverage existing MicroStation tools such as GeoPack and coordinate geometry. There is automatic horizontal and vertical data transfer between roadways, structures, drainage, and utilities. There is seamless and continuous updates when parametric data is changed, supporting efficient change management. I'm going to be specifically discussing that point later in the presentation. You can view your bridge layout in context of the true world. There is intelligent connection to design and analytics, including bridge design, rebar layouts, strand patterns, and vertical clearance. You're able to reuse existing data as well as repurpose that data for additional analysis. All these advantages increase efficiency, which saves in time and money. So these images represent the easy-to-use and intuitive interface of OpenBridge Modeler. This interface is similar to MicroStation and AutoCAD in that the ribbons and toolbars can be customized to meet whatever your preference is. We will discuss some of the primary design analysis and reporting tools, such as input report, create drawings, quantities report, and class detection. We'll also talk about some of the parametric definitions used to create substructure and superstructure templates. Another important tool we will be discussing is the clash detection tool shown in the top right image. The bridge clash detection tool helps mitigate risk by performing conflict analysis between the bridge and proposed or existing infrastructure, which saves time, helps eliminate errors, and reduce project costs. You can view clashes in 3D or in a table format, which can be a helpful tool used to check the model as well as perform quality control and assurance. This tool will also detect clashes with reinforcing steel and other embedments, as well as checking setback and vertical clearance requirements. And again, we will be talking specifically about the clash detection tool later in the presentation.
Throughout this presentation, we will continue to discuss OpenBridge Modeler and its capabilities. But first, I'd like to introduce you to Bentley's latest software, which includes OBM. This software is called OpenBridge Designer, or OBD. OBD consolidates the modeling capabilities of OpenBridge Modeler and the analysis and design features of Leap Bridge Concrete, Leap Bridge Steel, RM Bridge, RM Bridge Advanced, and RM Bridge Enterprise to meet the design and construction needs of all types of bridges. With OpenBridge Designer, you have the advantage of using a single comprehensive package from beginning to end of any bridge design project. You can use one product to create an interoperable physical and analytical model for both steel and concrete bridges that can be utilized throughout the life cycle of the bridge. The image on the left depicts the design, analysis, and rating of a typical bridge. These programs leverage existing MicroStation tools and interfaces. This is done by reusing civil data obtained directly from Bentley road products such as Geopack, Bentley Inroads, or MX Road, and import roadway information and ground data from XML files. The image on the right displays the capture of roadway geometry and topographic features, similar to the Polk Parkway slides that David will present in a few minutes. The first thing you'll do when working in a new project is create an OpenBridge Designer file. This file will contain the OpenBridge Modeler files, Leap files, drawing files, graphics, etc. Once you create a new OBD file, you will choose if your project files will be BIM workflow or standalone. A BIM workflow project must be done in the order of modeling the bridge in OBM and then exporting that bridge from OBM to Leap. If you are working in Leap and want to modify part of the bridge, say the footing depth, for example, you must update this in OBM. Notice in the top screenshot on this slide, the analysis button is not accessible. The BIM workflow option guides the user through the typical BIM steps. Alternatively, in a standalone project, OBM and Leap can be completely independent of each other, where you can model your bridge in OBM or directly in Leap. Notice in the bottom screenshot that the analysis button is accessible. You still have the capability to export between both OBM and Leap, but you don't have to keep the two connected.
Thanks, Callie. So one of the projects we really got to kick the tires on the software and really run it through the paces and try to use almost every feature that OBM is applicable to us is Polk Parkway Design Build Pursuits. So this is one of the example projects that we're going to talk about, and this was a pursuit for Florida's Turnpike. We were able to utilize OBM in several different ways, from graphics to design to analysis. OBM allows you to quickly and efficiently develop renderings for LOIs, LORs, and technical proposals. On this project, we modeled a two-span bridge with skewed substructures utilizing the existing MicroStation tools like Geopack and coordinate geometry. We used OBM to develop our structural quantities by using the bridge reporting tools. OBM can develop various types of quantities like multiple classes of concrete and rebar. You can also use it to develop independent cost estimates by manually setting the cost of the quantity. On this job, we used the FDOT area historical costs and compared prices against the historical statewide averages. We also used OBM to perform vertical clearance checks using the class detection tool within OBM. On this project, we were able to utilize one of the unique features of OBM, and that is the ability to use peer or foundation templates developed from the previous jobs. I will talk about this feature in more depth in a couple of slides. OBM is fully integrated with ProjectWise, which is a good tool to support distribution with other project teams. We developed 3D PDFs to facilitate conversations with our contractor as well as in our internal team meeting. These 3D PDFs are also supported on mobile devices like iPads and iPhones for those who don't have access to a computer or they're out in the field. Google Earth is fully integrated with OBM as well as XMLs, which provides real-world context for your bridges. At the time of this pursuit, we were able to use OBM for technical proposal plans. We were not able to use OBM for technical proposal plans, as at the time of this pursuit, the FDOT Workspace had not yet been developed for plans production. However, the program can still develop plan and section views as a base file with your bridge-specific line work. As you can see in this image, the OpenBridge model is not just a pretty picture, but is a real analysis and design tool. In this image, you can see the superstructure, substructure, foundations, and piles. You can also see the depth of foundations, which is used to detect conflicts or clashes, as the program calls it, with existing or proposed drains and utilities. On this project, our proposed bridge was adjacent to the existing Polk Parkway Bridge, so we used a digital terrain model, also known as DTM, of the existing bridge and the as-built plans to model the existing bridge for real-world graphical representation of these side-by-side bridges. One of the big questions we typically get is, how do you check your models? We found several different ways to check and QC 3D models. On this project, we used a bridge reporting tool to print the input report for check and QC of the bridge geometry and design. We also performed a visual review to assure no gaps or holes within the model, especially at the roadway and bridge interface. In order to develop the graphic shown on the previous slide, we had to perform a few steps. The image shown is a new proposed Polk Parkway Bridge next to the digital terrain data of the existing Polk Parkway Bridge. This shows the existing topographic and survey information, which was used to model the existing bridge, as well as develop graphics as we talked about on the previous slide. It is important to note, in order to develop graphics like the ones previously shown, you must have existing or proposed elevation information. You will use the existing aerials of the surrounding area and drape them over the existing vertical data. Once you've draped the aerials over the DTM, you can export the model to a graphic software program to put the final touches on your graphic. You can add features like different vehicles, landscaping, lighting, and even choose your ideal weather conditions. Graphic software may be time and computationally extensive and not available to everyone, so another way to develop similar graphics and get the real-world context of your bridge is to save as or export your bridge to Google Earth as a KML. Be sure to set your bridge to the correct geographical coordinate system, or else your bridge may end up in the middle of the ocean. There are also some vertical translation issues between OBM and Google Earth, so you may need to adjust your model vertically. And again, DTM or existing survey information is needed for modeling existing bridges. On this project, we wanted to analyze a couple different span arrangements as well as vertical profiles. Every change of the vertical geometry has an effect on the superstructure and substructure, as well as the designs of the remaining bridge elements. With each change of the vertical profile made by the roadway engineer, the OpenBridge model handled that change seamlessly, and it also carried that change through to the design software like Callie was talking about earlier. However, it is important to note that your bridge must be set up using the parametric definitions, or else any updates will not be automatic and will require manual adjustment. Once you've defined the bridge elements in relation to the alignment, the model will update the remaining bridge elements automatically. On this project, the changes were immediate, which obviously increases our efficiency and requires less intensive coordination between structures and roadway. Another tool shown in the left image was the pier templates. Pier templates allow you to develop substructures quickly and efficiently. This multi-column pier had been defined on a previous project and imported into this bridge model and site adapted. Template-based definitions are simple and easy to use and allow flexibility as you move from job to job. Templates can also be applied to beams and decks, which help when the roadway engineer will make changes to the cross slope or super elevation transition. Another good feature of this program is highlighted in the image on the right. Originally, the bridge substructure was modeled perpendicular to the superstructure in the proposed Polk Parkway, so there was no skew. However, the decision was made to match the adjacent existing bridge, so we decided to skew the substructure to be parallel to the existing roadway underneath Polk Parkway. We made this decision after the model had been developed. But because the model was originally set up with parametric definitions, which linked the substructure and the superstructure together, and all of that was in relation to the alignment, this allowed for intelligent updating and change management. With 3 clicks, we were able to change the skew angle of the substructure from 0 degrees to 8 degrees, and the OpenBridge model updated all the other elements automatically. So changes to the 3D model dramatically changed the associated 2D views. The substructure and superstructure were automatically updated not only in the model, but also in the design software. Another important note is that when we were modeling the bridge, specifically the bridge superstructure, due to the symmetry of the bridge, we were able to use the Copy To tool to copy superstructure definitions to the remaining span. Quantities, cost estimates, and bids are an important element of design-build pursuits. OpenBridge Modeler has the capabilities of reporting accurate quantities and quickly turning those quantities into a cost estimate. When you complete your bridge model, you will be able to get the quantities based on your defined superstructure, substructure, and foundation. The quantities report is simple and easy to use. This tool can be used to evaluate multiple substructure and superstructure alternatives based on your bridge model. You can compare different span arrangements with the click of a mouse. The steps are easy. Once your bridge model is complete with parametric definitions, go to the Analysis and Reporting ribbon, click Quantities Report, and then once within the report, you can import previously defined report formats, or you can define your own format. Once you've settled on a format, simply select your bridge or a unit of the bridge and click Submit. A report will be generated within seconds based on your selections and bridge model. This report can be used as a quick check on your model. For example, if you have an overly high concrete quantity or there is an outlier in the quantities, then you may need to review your bridge model. The report can also be used to develop quantity plan sheets or be submitted as a standalone deliverable. Currently, OBM does not quantify rebar. However, you can export the report to Microsoft Excel and insert a rebar ratio to complete your cost estimate. The cost analysis tool is very helpful with predefined unit prices. However, there are many instances in which you will want to change the unit cost to get a more accurate cost estimate. There are several ways to change the unit cost, and I've highlighted two here. One way to change the unit price is to export the quantities to Microsoft Excel. In Excel, you can change the unit prices within the individual cells and update the total cost formula to get a more refined total cost. It is important to note that when you export the report to Excel, it will only export as numerical values and will not have any formulas within the Excel. So you will need to update that, and those will have to be user defined. The second option is to go into the material library and change the unit price within the material library. Once changed, you can save that library, and you can also use it in the future. You can also import a materials library from one that you defined on a previous project or has your unit costs already built into it. And you can also export those as an XML. This is helpful if you're interested in modifying other material properties of the bridge element. As you can see there, if you want to change some of the other beam properties, structural properties, this is where you can do that.
Another example project is the Colonial Parkway PD&E. WGI was hired to do the renderings and animations for the preferred alternative of this entire job. We constructed a model that spanned 12 miles and included all the proposed and existing features of the corridor. This is an example of a fly-through of the job. This video spans the first quarter of the Colonial Parkway and has live traffic. In this video, you can see that we modeled all the existing buildings and landscaping. We coordinated with multiple divisions to bring this model to life. OpenBridge Designer and OpenBridge Modeler were utilized to bring all facets of the job together. After this video is concluded, I'll go into further detail about how each of the components were brought in to create a master model with all disciplines. This animation was used for a public hearing to show how the project would impact the daily lives of the public. People could find their street and/or house if they were close enough and see if the project would affect their daily driving pattern. We were given positive feedback from the public saying that this made the project much clearer to them than the roll plots that were arranged around the room did. Animations such as this one will increase public engagement and help answer questions visually. This technology has not only already proven itself useful, but will continue to be very important and beneficial moving forward with social distancing. The first step in the Colonial process was to use OpenBridge Designer to create the 2D plans, and then use corridor modeling to create a 3D model. Corridor modeling consists of creating templates, which are basically typicals. These templates are then extruded along the alignment and profile to create the 3D model of the roadway and its elements. With these templates, we can model the entire roadway, barrier walls, MSE walls, guardrails, and more. OpenRoads has a quantity component tool similar to OpenBridge, which makes it very easy to pull quantities from each corridor and give an estimate very quickly. Similar to OBM, OpenRoads has the capability of tabulating quantities for specific components throughout the project. The second step in the process was to create the bridges, which was accomplished using OBM. Once these bridges were modeled, they were referenced into the 3D OpenRoads model. The third step was to coordinate with signing and pavement marking division to get their line work and sign locations. The pavement markings were applied using a stencil tool in OpenRoads, which will take your 2D line work and overlay it onto your 3D model. The signs were coordinated to go in the correct location and with correct elevation. All signs were created using guide sign software and manipulated to appear on the sign panel in 3D. The fourth step was to construct the toll gantry and toll gantry site. Due to the Turnpike general tolling requirements, frequency, and vibration design criteria, the toll gantries were modeled utilizing a finite element software with the necessary design capabilities. It's important to note that OpenBridge and OpenRoads are not able to analyze or design toll gantries. Once the model and design were completed in the finite element software, we were able to export the 3D model to a MicroStation file and reference the MicroStation file into OpenRoads. Once the toll gantry was in OpenRoads, we were able to place it in the correct geometric location. Since OpenRoads and OpenBridge are able to relate to the real world, the gantry is represented in true context of its location. OpenRoads can be utilized to verify the toll gantry is meeting the horizontal and vertical clearance requirements with the roadway horizontal and vertical profiles. The last step is to create the surrounding areas of the model. For this, we use 3D freehand techniques to create the existing buildings and the existing terrain. You'll then export your model to rendering and animation software, such as LumenRT or Lumion, where you can create still photos or long animations of your model. If you have exported your model to LumenRT and have already added objects such as people or cars, but you need to make an update to your road or bridge, you can make these changes and re-export them into Lumen without impacting any changes you made within Lumen. Most animation software are also able to produce cubes. Cubes are a reduced version of your complete 3D model in a single file that can be delivered to anyone, whether or not they have the animation software on their computer. Within these cubes, the user is able to zoom in and out at any location along your model. Graphics can also be created to help make important design and construction decisions, especially for the construction of this box culvert. It included construction of 3 new concrete box culverts within the limits of 4 smaller existing concrete box culverts, while maintaining flow through at least 2 of the existing culverts at all times. The graphic shows the second phase of the TCP, where 2 existing culverts, which are shown in dark gray, are demolished and the 3 proposed culverts are constructed. As you can see, the 3D image on the right side gives a much clearer picture of what's happening during this phase of construction than the 2D image on the left. The 3D image helps show how traffic will continue to flow while this construction phase is taking place. These renderings can help foresee problems that occur before construction even begins. So here's a look at the graphic in OBM before you export it to LumenRT. OpenBridge Modeler's freehand 3D modeling tools, which are shown in the screenshot below the graphic, were used to model the box culverts and temporary walls and anchors. OpenBridge makes it very easy to create miscellaneous objects, at correct elevations and dimensions using the Civil AccuDraw tool shown on the bottom left of the taskbar screenshot. Within the OBM drop-down menu, the modeling menu has multiple tabs to help create solids, such as a box culvert in this example. First, a line was drawn from end to end at the invert elevations using the Civil AccuDraw tool. Then a 2D box was drawn at one end of the line to represent the outer shell of one of the culverts, and then it was extruded along the line to make a solid. Using the shell tool, the solid was hollowed out from end to end with a 10-inch thick wall. The anchors were created by drawing a single anchor in a separate model, saving that anchor as a cell, importing the cell into this model, and then once the anchor was placed appropriately in one position, it was extruded along a baseline that represented the sheet pile walls. The sheet pile walls were also created in a similar manner. I would like to point out that OpenBridge Designer does not handle anchor walls or box culvert analysis. Once the model was exported back into LumenRT, we were able to change material features such as the existing roadway pavement versus the proposed roadway pavement, the existing box culverts versus the proposed box culverts, and the soil. We also added vehicles and construction workers. To give the reviewer an even more in-depth idea of what's going on in this graphic, we added in red the roadway width that was proposed in the RFP. This clearly shows the cost savings that our proposed design offers compared to the RFP design. An important item to note here is how the MSE walls were created in 3D. MSE walls are created with templates in OpenRoads Modeler, not in OpenBridge Modeler. Since the roadway engineer has control of the templates within OpenRoads Modeler, coordination must be done between the roadway and structural engineers. The view on the left represents the profile of a leveling pad from this project. OBM has a tool called Open Profile View, which allows the designer to select any smart line in plan view, as shown in the view on the right, and view or manipulate its profile. Once you are in the profile view, it not only highlights the line in plan view that you're evaluating, but also points to the corresponding plan locations when you are using tools in the profile view. During this project, the roadway engineer was able to provide coping elevations, ground line elevations, and wall offsets to the structural engineer for the MSE walls. The structural engineer created profiles in OpenBridge Modeler for the leveling pads at each wall. The roadway engineer is then able to attach these profiles to their templates so that the leveling pads follow the correct profiles in the model and consequently in the cross sections. If the profiles were ever updated, the model in OpenRoads would automatically update to fit the leveling pad profile.
Thanks, Callie. So as we all know, 3D models help us evaluate complex situations that can be easily missed in 2D plans or in 2D views. On this specific project, I-95 Commercial Boulevard over Andrews Ave, we are going to highlight the clash detection tool and checking vertical clearance. On this project, the proposed bridge we were modeling had concrete beams supported by a concrete hammerhead pier over multiple existing roadways in South Florida. Each of the existing roadways has their own existing profile, which made the vertical clearance check not as straightforward. After we developed the OpenBridge model, we brought in the existing roadway digital terrain information provided by our survey team, and it confirmed that what the as-built plans were showing us in that each roadway had different vertical profiles. We performed the vertical clearance check using the clash detection tool, again, without performing external clearance calculations and doing repetitive data entry. This is going to be difficult to visualize if you're not meeting vertical clearance in a 2D view or in 2D plan sheet. With the clash detection tool, we were able to quickly verify vertical and horizontal clearances. It is important to note that you must user select objects and manually set the clash check criteria definition to whatever you want to check it against. So in this situation, 16.5 feet for vertical clearance. You can set this to any definition that you want. If you want to maintain existing vertical clearance at 16 feet, or if you wanted to check a sign structure at 17.5 feet, you can do that as well. This program can quickly check against the vertical profiles, or in this case, existing DTMs, to identify if the bridge is meeting the user-defined vertical clearance. As you can see on this project, the pier was overhanging the roadway and was not accounted for in the very basic preliminary profile, and thus the bridge was too low and it was identified as a conflict or clash. This is a much more efficient process and less involved than your traditional method. The program can also be used in a similar fashion to detect for subsurface utilities or drainage classes by changing the user definition. It should be noted that a drawback of the clash detection tool is that the program will identify a clash. However, it will not specifically define where the clash is occurring. You must still use engineering judgment to further refine your profiles or your clearances by identifying the critical clearance points. So on this slide, we wanted to demonstrate a few of OBM's graphical capabilities. So on these example projects, we were asked to develop graphics to show both aesthetics and utility conflicts. The image on the left is State Road 91 widening from Golden Glades to Broward County. On this project, the client asked us to depict the overhead power lines, the subsurface utilities, as well as their proposed aesthetics. The aesthetics were a very important part, especially to the public, and so there's a big public factor on this project, and that's exactly why our client asked for this graphic and this model depicting the bridge aesthetics. The freehand 3D modeling tool that Callie was previously talking about was used to depict both the bridge and the wall aesthetics you see here. The image on the right is from our FTE pilot project. This graphic demonstrates sign structure erection in proximity to existing overhead power lines. The overhead lines were modeled using existing DTM and LiDAR technology. We referenced that information into our OpenRoads file, and then within OpenRoads, we were able to create the transparent halos around the existing power lines and use those for vertical clearance checks and horizontal clearance checks. The green halo represents compliance with the clearance requirements, and naturally the red halo represents non-compliance with the governing criteria.
One of the add-on programs that Bentley offers is called Pro Structures. Pro Structures add-on creates accurate 3D models for structural steel, metalwork, and reinforced concrete structures. It allows you to create design drawings, fabrication details, and schedules that automatically update whenever you change the 3D model. This program can develop plans, details, sections, quantities, and cost estimates. Concrete objects such as footings, columns, beams, and slabs are automatically recognized for the appropriate tool in Pro Structures. We utilize this software on a turnpike project on the heft from State Road 836 to Northwest 106th Street. We use the program to model in detail a concrete inverted T, which lends itself to complex rebar layouts, where detailing and verifying clearance requirements is very complex. It should be noted that in order to utilize the clash situation, the applicable design criteria like AASHTO or the IBC you are trying to check the rebar clearance against must be manually defined in the program. The program does not currently have the design criteria loaded into it. We ran the clash detection tool within Pro Structures, and as you can see, the tool identified a clash and manually described clearance requirements as shown by the red highlighted reinforcement. In the next slide, you can see where the red highlighted reinforcement was manually modified to a 180-degree hook. The clash detection tool was rerun, and the user input clearance requirements were met and no longer detected a clash. This program allows you to analyze in profiles, elevation, and cross-section views with solid and transparent options to help you explore areas with complex geometry.
Now we're going to transition to talking about some of the challenges and lessons learned from our projects, pursuits, and even our designs. The first design challenge we wanted to talk about is how existing bridge information, digital terrain models, and bridge widenings are a little bit cumbersome within OpenBridge Modeler. So previously, structural engineers relied on as-built and 2D surveys to help determine existing bridge geometry. For bridge widenings, the traditional process started with recreating the existing bridge in 2D CAD using the as-built plans, and if we were lucky, we would also have topographic information. Now, once the existing bridge model is complete, we can compare the 3D, DTM, and LiDAR point cloud against the as-built plan. And once you finalize that model, it's ready for final design. For the existing bridge model, the DTM of the bridge deck surface is utilized to establish the existing top of deck elevation, the bridge's cross slope, the coping limits, and the begin and end bridge limits. This refinement in a 3D environment improves the accuracy of the existing beam locations, top of deck elevation, substructure geometry, orientation of exposed pile foundations, as well as proposed drainage, existing drainage, and utilities. These are all key elements in a typical bridge widening project. Knowing and seeing the location of all aspects of a project allows the design team to better identify constructability issues, like where am I going to place a crane or other geometric conflicts such as driving piles or other constructability issues. OpenBridge is best when modeling and designing a brand new bridge, but bridge widenings pose more of a challenge. For example, the existing bridge typically has different properties or dimensions than the proposed bridge widening. For example, the material properties, deck thickness, or beam types may differ within an existing bridge, and typically they certainly will differ from the proposed bridge. For design purposes, the program has limitations on these different properties, and that forces you to have multiple bridges and units. They have to be utilized to overcome this limitation and challenge. And with that, that will sometimes lead to slower processing speeds and potentially lead to your software crashes and even corrupt files. Currently, the best way to model a bridge widening is to create one file with the existing bridge model and a separate file with your proposed bridge widening. You can then reference both the existing and the proposed bridges into one master file from which plan sheets can then be developed. One benefit to having the file separated when progressing from modeling to design is that the existing conditions aren't typically necessary to design your proposed or new bridge. So as Callie presented earlier, Bentley's latest software development is OpenBridge Designer, or OBD. Due to the newness of the software, we have limited experience using this on current projects or pursuits. However, we have been able to demo it pretty extensively. The software and its combination of OpenBridge Modeler and LeapBridge design softwares like Leap Steel and Leap Concrete, like Callie had previously described. The program combines several supplemental programs into it as well into one product, which reduces repetitive data entry, and it will also reuse and repurpose other discipline data, which increases efficiency and saves time and cost. This software is preliminary and has been relatively untested by the mass market, so there may be additional bugs or obstacles to overcome, but so far our use of the program has been relatively seamless and efficient without too many crashes or corrupt files or lost effort, and we're seeing some pretty good translation between the programs. One important note is that when using this software, when you go from exporting from OpenBridge Modeler to your analysis software like Leap Concrete or Leap Steel, you will receive the model transfer report. The model transfer report gives a summary of the assumptions and translations between the different programs. This is going to be really important for all parties to review and be comfortable with how the programs are communicating. So in our situation, we performed some additional checks and reviews to make sure that the geometry was communicating and translating properly between the multiple softwares.
One of the important topics that we wanted to cover was planned production capabilities of OpenBridge Modeler. However, it's still in the beginning steps of development. FDOT recently released the CAD manual updated to support the FDOT design manual for FDOT Connect and FDOT 2021 C3D. However, like David mentioned earlier in the presentation, the plans production process has not yet been finalized nor perfected. The beta version of the FDOT OBM Workspace was released with the FDOT Connect July 2020 maintenance release. The image found at the bottom of this page was created by OpenBridge Modeler. We used the tool called Create Superstructure Cross-Section Drawing under the Analysis and Reporting ribbon. As you can see, it does a pretty good job creating a section through Bridge Deck and exporting the bridge geometry. The beta FDOT OBM Workspace release is not intended for production, so in the meantime, this baseline work can then be copied into an FDOT CAD workspace, manipulated, and modified to meet the FDOT CAD manual standards. Similarly, substructure and foundation baseline work and base files can be developed using the Create Substructure Drawings tool found under the same Analysis and Reporting ribbon. Again, like the superstructure, additional manipulation will need to be performed. As described, OpenBridge Modeler allows you to generate detailed reports as well as create 3D models and 2D drawings for sections, elevations, and framing plans. The image above from Bentley depicts taking a multi-column concrete pier and developing the plan view, elevation view, section views, and even the foundation views. Like I previously described, you would then need to manipulate the resultant CAD to conform with the FDOT criteria or the applicable client requirements.
Obstacles that are needed to overcome. So one of the biggest obstacles, and for very good reason, is the generational pushback. We've encountered a hesitancy to fully adopt a 3D bridge model as the main source of design in plans production. There are many in our industry who have been using the traditional bridge design method for many years, and trusting a new process is difficult. There's also the learning curve associated with a new program and fully buying into a full 3D design software. We found, as with any new software, once we've been able to compare the OBM results with our existing spreadsheets or our existing tools, the hesitancy that we initially encountered, it begins to dissipate. Switching the entire process to 3D is difficult, and it definitely has its own issues associated with it. It's a different way of learning and visualizing plans, and that's not easy. There's also the obstacle of staying up to date with the most recent developments in this advancing technology. Bentley is constantly releasing new updates, new versions, and especially with the plans production side of it, they're constantly trying to do better, trying to get better with their workspace. With that being said, we found some issues with the use of newer and older versions of the same software. So the same OBM, the same OBD, but different versions. We've experienced this within WGI as well as when coordinating design files with other consultants. So our recommendation is that additional coordination should take place to assure that those on the same project are using the same version of the software. If not, you can find yourself corrupting files because they're not backwards compatible. For example, if you wanted to send your OBM file for someone to check either outside your company or even within your own company, and they are using a newer version of the software. Once they open that file, you will no longer be able to open that file once they send it back to you on your older version. So then you would either need to upgrade your version of the software, or you would have to start the file over from scratch. One practical solution we found useful is to make sure everyone is using the same version of the software, obviously, and then we all agree to not update the version unless we all kind of agree and we all take count of our own projects and we all agree to update the version. With that being said, sometimes you have some projects that are older and were designed using an older version, in which case we've kept those specific projects and the team members working on those projects with the same older version and the same version. And we won't update their software until that project is completely closed out. Another challenge is developing an accepted form of quality control and quality assurance. Most government agencies, as well as the Florida board, are investing resources to develop a form of control that demonstrates supervision, checks, and quality assurance. As of now, there is not an accepted way to QC a model. We are continuing to aid these agencies in their development of QC processes and assurances. These processes must ensure the highest quality and safety of that the traditional design and plans production was giving the public. The Florida Board of Professional Engineers is another obstacle to overcome in this progression to a 3D world with 3D models as the main source of design and plans production. How we ensure supervision, liability, and ownership for engineers of record in the board's eyes is going to be a very challenging task. However, the Florida board understands the DOT and the agency's desires to ultimately make 3D models the contract document, and they've had ongoing discussions over the past year regarding this specific topic. Most recently, the board has created a task force to explore rules and assurances for sign and sealing multi-dimensional or 3D electronic models.
To summarize the highlights of our presentation, there are a number of great benefits to using OpenBridge Modeler and OpenBridge Designer, including converting roadway and bridge information into graphics, videos, and 3D PDFs. The program also helps you visualize in 3D, 2D issues or conflicts that are commonly missed. There's an automatic data transfer between the disciplines. You get to see your bridge in context of the real world. You're reusing and repurposing data, which results in time and cost savings. You also get to leverage existing MicroStation capabilities like geopack and coordinate geometry to create accurate bridge models that update and change as the roadway information changes. Some of the challenges we've experienced are FDOT CAD manual criteria being integrated into OpenBridge Modeler. There are some generational obstacles that we will need to overcome in order to continue designing bridges in OpenBridge. The Florida Board of Professional Engineers still need to sort out how to delegate and document EOR responsibilities, as well as figuring out how to perform peer review checks, quality control, and quality assurance. As we noted, there are also some design limitations that we discussed, including bridge widenings, utilizing existing topographic information and LiDAR, and cross-software program communication. And with that, I'm going to turn it back over to Stephanie for Q&A.
Thank you so much. We do have a few minutes for if anyone does have a couple questions. Again, there is a questions feature with GoToWebinars where you can submit any questions, or you can use the chat feature. As we wait for any questions, I'll remind the audience that at the close of this webinar, there will be a survey that we ask you to complete for all of your, for anyone interested in getting PDHs. Please make sure that you complete that survey in its entirety, and it will take approximately 7 to 10 10 business days for us to process those and send out an email regarding instructions on how to access your certificate. Wait a few seconds to see if there's any questions today.
While we're waiting, Stephanie, one of the common questions that we typically have gotten is, what is the learning curve, or how long did it take for us to kind of get up to speed with this software, and what kind of training we did? That's a very typical question that we get, and so we just kind of want to share that information. We've done some internal training that are 1 or 2 days, sometimes on the weekends, where a group of us will get together and we'll do some of the training on example projects, or we'll try to take one of our projects that had already been designed and do the full thing in OpenBridge Designer and OpenRoads, and really try to work out all the kinks and issues that we were finding. And that way, when we get to a project that we've won, we're able to efficiently design and model that using OBD and ORD. Callie, did you have anything to add on that?
No, yeah, you pretty much said it. It's pretty straightforward, intuitive software to learn, but there are a lot of things that you can do with it, so you can get pretty lost in a lot of nice, good tools, very useful tools for designing and analysis.
Yeah, that's a great point too, is that it is very similar to MicroStation, and for those that are very comfortable with MicroStation, the interface and the ribbons and the tools are very similar, and some of them are the same, like we alluded to early in the presentation. So it doesn't take a whole lot of effort to really get up to speed with this software.
Thank you so much. I did get a couple of questions in. So the first question is, what are the challenges with both FDOT and Bentley making software updates and the resulting compatibility issues?
So I know in our experience, the way we've seen it is, like we said, once you kind of start using one version of the software, and then the FDOT releases, or not, either the FDOT and Bentley combined will release an update to the Workspace. Getting that worked in and kind of updating everyone's software is sometimes a little difficult and sometimes cumbersome, and we've lost a little bit of work in doing that. But once you get those updates in, you've updated everyone's versions of the software if you're able to. We've seen pretty good compatibility. The only issue, like we talked about earlier, was the backwards compatibility, trying to have different versions of the same software and opening the file. Once you open it in a newer version, if you try to open it again in your older version, it won't allow you to do that. So it's definitely, it takes a little bit of organization to make sure that everyone's using the same version and that you have agreement before updating everyone's version of the software.
Mm-hmm.
Thank you so much. And the second question that we got submitted was, how will OBM work with FDOT FBMP, or is there no interaction at all? Do I need to repeat that?
Well, that's a good question. I know that the FDOT is working constantly on, they have been working a lot with Bentley and creating the Workspace and all. I'm not sure about the other ones, but yeah, they are trying. I know FDOT is working hard to get their Workspace going with Bentley as much as possible. So.
All right, thank you so much. I know we are just about out of time. Oh, let me get this one last question in and then we will wrap up. From an efficiency perspective, would it be better for the software versions, both FDOT and Bentley, to be established at the start of the project?
Yes, especially, yeah, that's a great point. That's how we've done it in the past, especially on like pursuits or whether we're starting a design from on the conventional side. We kind of will, as long as there's no updates that are correcting, a big fatal flaw or making, fixing something that is wrong with the program. If it's just kind of making it more efficient or something like that, we'll stay with the agreed upon version. And then there have been 1 or 2 times where there's been this massive, they've released an update that fixes a lot of more of this more serious issues. And so in those situations, we kind of get consensus, we all talk and make sure we're all in agreement to, especially within your internal design team, to upgrade everyone's version of the software.
Mhm.
Thank you so much. Well, I would like to again thank our speakers this afternoon for their presentation and their time. And we hope that everyone has a lovely afternoon, and we look forward to seeing everyone at our next webinar next Tuesday. And with that, have a wonderful day. Thank you.
Thank you.
Thank you.